Spresso and how to set up some basic electrophoresis simulations such as isotachophoresis and capillary electrophoresis. So we start here. This is the Spresso main screen, the graphical user interface. And on the bottom left, you have the list of chemicals or analytes you can use in the simulation. This feeds from an Excel file, which is located under the database folder of the main Spresso folder. So let me choose acetic acid, say it's the first one in the list. You can scroll down, you can see the valence and mobility and pKa's of each of the analytes. I'll choose acetic acid and click Add. It adds it to the list on the right. Let me add a couple more. Okay. And now let me show you how to change the properties of this chemical, since obviously I don't want to run a simulation with only acetic acid. So let's go for a simple isotachophoresis simulation. So I'll change the first one to be the Le, leading electrolyte, and change its concentration to be 0.1, so that's 100 millimolar. And you can see the profile changing here in the main figure. Second one will be the Te, the trailing electrolyte. Let me change the concentration to be 0.05, so that's 50 millimolars. This is still set to Le as the profile, so we'll change it to Te. And we'll also need a counter ion. And let's set the value as 0.15, so 150 millimolars. And again, change the profile to background, so this sets it just as a uniform distribution in the background. Last, let's add an analyte that will focus between the leading electrolyte and trailing electrolyte. So let's call this analyte. And let's put values of 0.01, so it'll be 10 millimolars. And the profile will be analyte. So now you can see this small bump here at the interface. I did one too many, so let's hit the remove button, and that simply removes it from the list. The injection point determines the location of the interface between the different chemicals. So if I change this to say 7, you can see everything is shifted to the right. Bring it back to 5. The injection width determines essentially the length of the injection for the analyte. The best is just to show how it works. So if I change this to 5, you can see that the analyte spreads over 5 millimeters, and there's of course also a diffusion region. If I increase the length of the domain, put this as 100 and increase the number of grid points, and move this to the center a little bit and increase this to be, say, 15, you can see more clearly what this does. Okay, so we'll go back to 100, 10, bring this back to the center as 5 with a width of 1, and we're almost set. But I changed only the names of the different chemicals and not their chemical properties. So if you want this to work, we need to make the leading electrolyte faster, the trailing electrolyte slower, the analyte somewhere in between. So let's change the mobilities. This needs to be faster, so let's put this as a 6. Trailing electrolyte can be slower, so we'll leave it as a 4. The counter ion, that doesn't really matter. Let's put it as 3. And of course change its valence to +1, so it will be positively charged. And let's put the analyte as 5. So this is somewhere between 6 and 4. And all of them have currently the same pKa value, so they should be dissociated to the same extent, and so this will be the order of mobilities. This is a good point to look at some of the other options in the figure. So you can look at pH, for example. You can see the distribution of pH. It varies from about 4.9 in the leading electrolyte region to about 5.2 in the trailing electrolyte region. If you look at the effective mobilities, so you can graphically verify that everything is set up correctly. So yes, the Le is faster than the counter ion, than the analyte, which is faster than the trailing electrolyte, and the counter ion here has an opposite sign for its mobility. So everything looks good. We'll go back to the concentration. And now before we run it, let's save the file. So we can't use save yet because we haven't specified a file name. we'll click on Save As. Let's go to Input File and call this my ITP, my first ITP sim. I made this file before, so I'll hit Save. And now ask me whether I want to replace it. Let's say yes. And now we're good to go. So it's set, the current is set to be 1 microamp. And this is a circular channel with a 50 micron diameter. And we can hit Start. So when the simulation starts, you can see the adaptive grid kicks in and cluster grid points at regions of high gradients of concentration. So you see the ITP is forming. You can see the cold-rush adaptation of the trailing electrolyte. You can see this transient wave moving out of the domain, and you can see the analyte focused in between. You can see that there are many grid points here at the interface, and that the flat regions are very sparsely gridded, and this is the adaptive grid. This simulation currently runs on only 100 grid points. So let's stop this. If we hit Stop and Discard, then we're not saving anything right now, and once we hit Start, we'll start again from the very beginning. So I'll hit Stop, Discard again. Let me go to a slightly higher current, so I'll show you that the simulation behaves differently. Let's go to 3 microamps. If I hit Start now, actually I can't hit Start now because I haven't saved it yet. So I'll save the file first, then I can hit Start. So again, the same thing happens, only that the current density is now higher. So the interface should be much sharper than before. And indeed, you can see that this is the case. Now I will hit Stop Save to show you what happens. So once I hit Stop Save, I saved a .mat file, which has the same name as the input file. So it will be my first ITPSim.mat. And that contains all the information about the concentration, pH, the current time, and so on in the simulation. So I can now start from the point I stopped the simulation before. If I click Now Start, again it will start from the very beginning. Stop Discard. I'll hit this load mat checkbox. And now if I hit Start, it will start from the last location. Now I can continue running the simulation. Another example, if I hit Stop Discard Now, it did not save the information. I hit Start with this checked. It starts again from the last location. So let's stop save at this point. By the way, you can see that as I'm clicking on different things, you have some tips here in the message box that it will tell you how to operate the different buttons and what you should expect the influence to be. Also, if you hover with your mouse on any of these, you'll get some very short tooltips that can remind you what each one of these does. Okay, so this is a very simple ITP example. And now let's look at a simple capillary electrophoresis problem. So I'll load a file. I have this simulation ready. We'll go to Input Files and choose, it's called CZE Demo. This is now a little slower than real time because of the capturing software running in the background. But here it is loaded. And you can see that everything looks uniform. This one is the bistress, which acts here simply as a background buffer, and together with acetic acid. And if we zoom in, so click here on the plus, zoom in to this region. Again, this behaves a little strange because of the capturing program. You can see this peak. And this peak corresponds to several analytes that we have in place. So I'm going to release the load mat to start from a clean start, and hit the Start button. Again, the adaptive grid works, brings grid points to the right place. Now the simulation starts. You can see the peaks starting to separate. They have, again, the same pKa, just different mobilities. And they all start to spread. This simulation is currently running on a 200 millimeter domain length, so 20 centimeters channel, with only 200 grid points. And the reason that's possible is, again, because of the adaptive grid. We're not wasting any grid points in these flat regions, and all the grid points go to the interesting regions where the analytes actually separate. So you can see the process here. I'll hit stop discard. And let's look at some of the other options that we have here. Let me start running this again so we'll see something dynamic and changing fast. So we looked at the pH and the effective mobility. Let's look at the pH again. So this is a good example. We're zoomed in from before, so I'll have to right click here and reset to original view, otherwise we can't see anything. Okay, so here's the pH, and it's around 6.3, which is not surprising. Okay, let's look at other things such as the electric field. So you can see the electric field distribution around along the channel. So we have around 350 volts per meter here. It's a pretty low electric field. The conductivity. And also important is the grid density. Here we can get some information about the adaptive grid. And the maximum grid density currently is about 3. And this is the region of where the analytes are currently separating. And this means that locally the number of grid points is 3 times higher than when we started with a uniform grid.